Hey everyone, welcome back to the next session in our RAG series. In the last session, we explored the full retrieval pipeline starting from loading embedding model, storing document vectors in a vector database, and running similarity search to fetch relevant context for a given query. Now that we can retrieve context effectively, it's time to build a second half of RAG system, which is generator model. So in today's topics, we will learn about prompt template and LLM. Let's start with the basics. What exactly is a prompt template? A prompt template is a reusable and structured text format designed to guide the language model in how to respond. It consists of two parts: static instruction, which tells the model what kind of response is expected, and a placeholder, where a variable section where we inject user inputs, questions, or context dynamically. For example, consider this prompt. Here, the instruction is clear. We are asking for a summary, and paragraph text is a placeholder where the actual content will go when model is called. These simple structures allows us to reuse same prompt logic across multiple queries just by changing the input. Now that we know what a prompt template is, let's talk about why it's worth using them, especially in real world applications. First one is consistency. A prompt template ensure consistent language and instruction across all inputs. Whether you are asking the model to define a concept and summarize a passage, using standard template means the format stays the same. And that leads to more predictable and reliable responses. Second and most important point is reusability. A well designed template is reusable. You don't have to rewrite the prompt every time. You just change the input variable like the question or context and the rest is intact. This saves time and reduces errors. Third and last one is scalability. If you are building a system that handles thousands of queries a day, prompt templates are a must. They allow you to plug in new inputs programmatically while keeping the behavior of language model uniform and controllable, which is especially important in production pipelines. So whether you are doing a RAG, chatbot development, or automated document processing, prompt templates gives you structure, control, and scale. Now, let's look at some real examples of how prompt templates work in action. Consider these two queries: define superposition and what is quantum computing. In both cases, we are using structured prompt template, not just passing the question directly to LLM, but wrapping it inside a consistent format. Here is how we break it down. There is a combination of system level instructions and customizable guidance. It defines the role of model. Example, you are a quantum assistant and sets behavioral rules like using only the given context and avoiding assumptions. Second one is a context which comes from retriever. It's a relevant chunk of information retrieved based on the query. And third one is a question. This is user's original query. The part changes each time. And lastly, we have answer. This is just a placeholder, the actual spot where the LLM will write the response based on both context and the instruction. This structure helps ensure that model responds accurately, consistently, and grounded in retrieved information, not just prior training. Let's now build the prompt template for query 1, define superposition. We start with the header, which contains clear system level instruction. These guide large language model to stay focused, avoid hallucination, and answer strictly based on the given context. In this case, we also include instruction to keep the definition concise and limited to one sentence, ensuring clarity and precision. Next come the context. This is information retrieved by the retriever that's relevant to the query. Then we include actual user question, which is define the population. And finally, we leave a space for the LLM's response, which will be generated based on the context, question, and instruction provided. This structured approach ensure consistent and high quality answers in our RAG pipeline. Now let's apply the same prompt structure to query 2, which is what is quantum computing. Most of the template remain the same. We still have system level instructions to ensure the model avoids hallucination and stick to the retrieved context. The key difference here is the instruction line within the header. Since this is what question we update the instruction to, give a comprehensive and fact-based response to the following question. This small change tells the model provide more detailed answer compared to the earlier query where we asked for a short one-line definition. This demonstrates an important idea. We can design different prompt templates depending on the type of query. For example, one for the definition type questions, another for what and how questions, others for yes no comparison or even step by step explanations. In our project, we have used single consistent prompt template that performs well across different query types. But as a best practice, we recommend testing different templates and then deciding whether a single universal prompt works for you in your use case or it's better to customize per question type. So now that we have understand what prompt templates are and how they work, let's explore how to create high quality prompts using a trial and error approach. Prompt tuning is an iterative process. We don't always get the best response from the model on the first try. So we refine the template step by step. As a first step, we start simple. Then we evaluate the output. Then we refine the template, then test variations, and finally lock what works. So this is an iterative process. Pro tip is document each version and the result. This makes it easier to identify what changes, improved accuracy and style. Now that we have built our prompt template, complete with instructions, context, and the user questions, it's time to move on to final stage of the pipeline, passing the prompt to LLM. The language model takes all the structured input we have prepared and generated responses that's bounded in the relevant context shaped by the instruction in the prompt relevant to the specific user query. So let's dive into how this generator component works and understand LLM produce responses in the RAG system. As we know, a large language model is an advanced AI system trained on massive amount of text data to understand, interpret, and generate human-like language. In this session, we won't go deep into how large language model works internally, but keep in mind that LLM takes in along with relevant context and generate a response based on both instructions and the context provided. With that understanding, let's move on straight into a specific model we have used in our project. For our project, we are using Google Gemma 2B8, a compact yet capable LLM developed by Google DeepMind. Similar in design to GPT style models and contains 2 billion parameters, making it lightweight enough for local and low latency inference, but still powerful enough for high quality responses. The model is trained on high quality English and with web documents, and it's instruction tuned, which means it's optimized to follow human instructions accurately. It's a great fit for tasks like retrieval augmented generations and academic Q&A. Exactly the kind of structured queries we are using in our RAG setup. We chose it because it strikes great balance between performance and practicality. It is lightweight enough to run efficiently on your own hardware or with minimal cloud resources. It's been instruction tuned, meaning it understands and follows templated prompts very well, which is critical for structured generation in RAG systems. And perhaps most importantly, it is openly licensed. So you can experiment, fine tune, or extend it for your own use cases without any restrictions. Alright, now that we have covered every key component of RAG system, time to tie it all together. You understand how the retriever, prompt template, and LLM work individually. Now we will see how they come together in a code to form a fully functional RAG pipeline. Let's dive into Python implementation step by step. Before diving into the code, let's first understand objective of this project. We aim to build question answering system using RAG framework. We will use curated set of quantum computing nodes as our knowledge base, retrieve relevant context based on user query, and generate accurate answering using language model. This project demonstrates how RAG enables efficient domain-specific Q&A system by combining information retrieval and language generation. Let's begin with the first step, where we will build end-to-end RAG pipeline step by step. In this section, we will start by importing the essential libraries required for our project. We will also authenticate the Hugging Face hub, the models, and tokenizers. You will need a valid Hugging Face token to use pre-trained models. Just go to your Hugging Face file, settings, and paste it here. Now, we will load the embedding model and read the preprocessed version of the quantum computing nodes. The preprocessing step, like cleaning and formatting the text, was already completed in our previous session. So here we directly load the clean data and prepare it for the embedding model. We have also already covered this part in our previous session where we split the text into smaller chunks, generated embeddings using the model, and stored them in a Chroma DB for efficient retrieval. Now, as the next step, we will download the LLM and load it using Hugging Face Transformer library. This will allow us to pass our prompt, including the instruction, context, and user query, directly to the model for generating responses. Now that we have both LLM and the vector database in place, we will move on to the retrieval step. We will use a helper function that performs similarity search on the vector store using the user's query. This function will extract top 5 most relevant chunks, combine them, and use the result as the context for the prompt that we will send to the language model. Next, we use our universal prompt template, which we have carefully designed and refined through multiple rounds of trial and error. The user's query is inserted into this template along with the retrieved context and predefined instructions. Then we pass complete prompt through an LLM pipeline which generates structured and accurate response based on the context. Once we receive the generated response from LLM, we will parse it by splitting it into different components: the context, the question, and the answer. We will then store these parts into a dictionary which will help us organize the output for further use, such as displaying it on the UI or saving it for evaluation. Finally, we will print the question and the answer to verify model response. After creating our response generation function, the next step is to define a list of user questions. We will pass each of these questions through the function we just built, which handles context retrieval, prompt construction, and LLM response generation. This allows us to run the full RAG pipeline on a multiple queries in a clean and modular way. Let's review a couple of answers generated by our RAG system. So question 1 is, what are 3 reasons to study quantum computers? If you read the answer line by line, you will see this is a great response. It's well structured, clear, and directly answers the question with 3 strong points, just as prompt requested. The primary objective of this notebook was to create a vector database from our preprocessed quantum nodes and design and test universal prompt template that consistently produce accurate responses. With this foundation in place, we are now ready to move to the next notebook where we will build a complete RAG pipeline combining retrieval and generation seamlessly. That next step will give us glimpse of how this system could operate in a production-like setup where user queries trigger the end-to-end flow from vector search to response generation. So let's move on to the next notebook. Welcome to the second notebook, where we will implement end-to-end RAG pipeline using everything we prepared earlier. We will start by importing essential libraries and then load LLM model, which will be used to generate responses based on the retrieved context and our prompt templates. This notebook brings everything together and simulates how complete system would function in real world or production environment. After loading LLM and setting up the response generation pipeline, the next step is to load vector database we created in the previous notebook. This vector store contains all the embedded quantum nodes, which we will use to retrieve relevant context for any incoming query through similarity search. With both the retriever and generator ready, we now have all the components needed to build full RAG flow. Now we move on to the helper function, which is identical to the one we created in the previous notebook. This function takes a question, retrieves the most relevant context from the vector store, builds the full prompt, and gets the response from LLM. Using this, we will now test the complete RAG pipeline by running it on same 10 sample questions we used earlier. This will help us verify the entire flow from retrieval to generation is working as expected in unified pipeline. As you can see, we are getting similar responses to those generated in the previous notebook, which confirms that our stored vector database is working correctly and the retrieval is consistent. With that, we have now covered the full RAG pipeline from document preprocessing and vectorization to prompt templating, retrieval, and response generation using the LLM. This end-to-end setup not only demonstrates how a real RAG system operates, but also forms a strong foundation for deploying custom question answering system on domain-specific data. That wraps up the complete code walkthrough of our RAG project. If you'd like to explore the code, make modification, or try it with your own data, the GitHub repository link is provided in the video description below. Feel free to fork it, experiment, and build your own domain-specific RAG system. Before we wrap up, here are a few key recommendations as you build and scale your RAG systems. Keep your prompts modular, start simple, then scale, and experiment with different models like Minstrel, 7B, and Fee2. These practices not only improve flexibility and performance but also make your system easier to maintain and extend it in a long run. Today, you learned how to build fully functional retrieval augmented generation system, from setting up embeddings and vector stores to designing prompt templates and generating answers using an LLM. In the next sessions, we will continue to explore more advanced topics and build on top of this foundation. If you found this useful, feel free to like, share, and subscribe. And don't forget to check out the GitHub repo link in the description. Until next time, keep learning and keep building.